Next, we'll explore the pyramid as I introduce you to the postulates of quantum mechanics, examining how qubits and quantum systems are measured, and the role of Schrodinger's equation. So, according to many sources, there are various number of postulates of quantum mechanics, but the most commonly cited number are 6. So these are the 6 postulates of quantum mechanics. The first postulate is a quantum state is represented as an element of some inner product space. So that is a type of vector space. More specifically, a Hilbert space. So it's basically a nicely behaved vector space that supports some form of an inner product. So let's say an example. So cat psi can be thought of as, let's say, coefficient 1 psi of 1 plus coefficient 2 psi of 2. Now here's a qubit example. So let's say qubit could be seen as root half of 0, 0 plus half of 1, 0 plus half of 1, 1. So this is a particular state in a 2-qubit system. Each element is represented by a cat. And also it supports the inner product. So the inner product would be some scalar. Let's go to the second postulate. The second postulate states that any observable quantity such as mass, position, and momentum, any observable quantity, let's call this A, for example, you can think of could be position, momentum, and energy, spin, so on, is represented as an operator acting on a cat. Which represents a state. So for example, we have an example called A of psi. So this A provides something like the energy level of a quantum atom, the energy levels of the electrons. The electron systems is represented as a single state, psi. Then we have an example called H, so Hamiltonian, could mean p squared, or twice of m, twice of the mass, plus v of x. So it could be half of m spring constant analog and then x squared. This represents the Hamiltonian of oscillator. So harmonic oscillator, which is just a fancy word for like anything that moves like a spring. And the Hamiltonian gives us the energies. H is conservative and gives information about energy. If you want to solve the momentum or the position, you have to isolate p and x respectively. Let's move on to the third postulate. Third postulate says that okay, the second one is about the observables. The third one is about the eigenvalues. The outcome of observing some observable metric, let's call this A, can only be one of the eigenvalues of its corresponding operator. Corresponding operator A hat. So here's the thing. What is an eigen? What is an eigen? What is an eigen? So an eigenvalue is basically a scalar associated with a particular state, which when operated by the operator A, only changes the coefficient. It's only scalarly transforms the ket. So we have this. A of psi is equal to lambda of n of psi. Implies that lambda n is one of the elements of the sample space. So here is an example of an eigen in action. And this has to do with the very notion of a basis, the z basis, the computational basis. So consider a two-qubit system in the state psi. Let's say the state psi is of the form half of 0, 0 plus half I of 0, 1 plus minus, let's say minus half of 1, 0 minus I have of 1, 1. I believe you can easily do this with only S gates and control gates to create this state. But then you want to measure the qubit pair. So qubit pair is in the state psi. The only measurable outcomes, the only outcomes you can actually see when you're doing one shot is this. So shot outcome has to be like a 4-element set, namely 0, 0, 0, 1, 1, 0, 1, 1. That means the superposition state, the plus state, which is equal to root half of 0, so plus 0, 0, 0 plus root half of 1, 0 is not in this outcomes. So you cannot observe and get a result of plus 0, like anything that is outside of these four. Namely, there is actually a very specific operator associated with this. This is nothing more than the z basis. So z is the observable. So we're measuring it in the z basis. That's called the computational basis. Eigen pairs are this. Eigenpairs are plus 1, which is associated with the 0 state, and minus 1, which is associated with the 1 state. So highlight this over there. We will explore the x basis and the y basis somewhere on the second or third ring. Most likely on the third ring. The fourth postulate is about measurement probabilities. So let lambda of n be one of the eigenvalues, so or outcomes when measuring a quantum system. This is where the notion of probability comes into place. The probability of having realizing lambda n as a measurement outcome on a quantum state that state psi is given by the squared norm of the inner product between the current state and the eigenvalue, corresponding eigenvalue, eigenket, the corresponding eigenket. So that means probability of lambda n given psi, so measuring that, which lambda n is one of the eigenvalues of A, is equal to this inner product, let's call this A of n, which psi, then take the absolute value and square it. And one thing about this is this thing appears to be nothing more than a Pythagorean addition. So let's examine a system that has been undergone an RT gate. We've talked about in a previous session. Let's consider a system in the state psi. So psi is equal to 2/3 of 0 plus 1/3 of 1. So 0 and 1 are the eigens. Now, let's just make it a bit more complicated. Let's try to do it as I. Now we have 1 over psi would mean the 0 term is cancelled out. Now we would end up with just I over root 3. Now we take the square norm of that, so root 1 over psi squared is just I would have a square norm of 1, and then root 3 would have a square norm of 3. So this is an example after applying a RT gate. Number 5. Number 5 states the nature of the quantum system after observation. After observation and realizing the outcome lambda n, the state of the system collapses to to the normalized eigen vector. Let's call this alpha a of n for eigen value lambda of n. So here is an example of the plus state. So let's say we have a system in the one state, and we want to measure it in the x basis. So what are the eigenvalues of x? It's namely the plus state and the minus state. Namely, 1 can be expressed as this. 1 minus 0, 1 plus 0 halved, plus 1 minus 0 halved. This thing can be expressed as 1 over root half of the plus state, and this is just the negative of 1 over root half of root 2 of the minus state. Sorry, I got root half and root 2 a bit mixed up. So 1 can then suddenly be expressed using a change of basis to 1 over root half, negative 1 over root half in the x state. So 0, 1 in the z basis, root half, negative root half in the x basis. Now we measure this thing in the x basis, and then we end up with the result of minus 1. So we got like a minus 1 as a result. That means the 1 must collapse to the minus state upon measuring the qubit in the x-axis. Lastly, the sixth and final postulate is the Schrodinger's equation. The time evolution of a quantum state is determined by the Schrödinger differential equation. Determined by the Schrödinger equation. Equivalently, the state after some time t is a unitary transformation of the fiducial or initial state. So these are the two equivalent equations. So imaginary reduced Planck derivative of the system is equal to the Hamiltonian operator acting on the system, which the Hamiltonian also has to be Hermitian. So H is called the Hamiltonian Hermitian operator. It is a Hermitian operator. So it's a very special form of a linear operator. Or equivalently, psi at time t is equal to a unitary varying operator acting on psi. So this is the sixth and final postulate. We'll explore about the Schrodinger's equation after Quantum Odyssey, because Quantum Odyssey we will not explore much about this phenomenon. Finally, we will conclude this with a demonstration of entanglement. So entangled state. So let's consider this state. We have psi is equal to, let's say, root 2/3 of 0, 0 plus 1 over root 6 of 1, 0 plus 1 over root 6 of 1, 1. So this is an example of an entangled state. So why? This is because there is a 2 in 3 probability of realizing 0, 0. So probability of 0, 0 is 2 over 3. The probability of realizing 1, 0 is 1 over 6. The probability of realizing 1, 1 is 1 over 6. But here is the thing. The probabilities are not independent. That means the probability of observing the first 0 and then the second 0 is actually dependent. Namely, probability of receiving another 0 given 0 is actually unity. So especially if, let's say, 0 on the first qubit, 0 on the 0th qubit is 1. But the probability of observing a 0 on the 0th qubit, the right qubit, and a 0 on the first qubit over there is only a half. Nope. It's actually, so there's now 5 distinct possibilities. So it's going to be 5/6. So 2/3, so 4/6 and then 5 sixths. So there's only like 5 possible ways. So it's 4/5. So here's a calculation for that. So 2/3 plus over 2/3 plus 1/6. This makes up to be 5/6, and then this is going to be 4/6, so 4/5. Likewise, the probability of observing a 1 on the right qubit given a 0 on the left qubit is actually 0. Observing a probability of, and likewise observing a 1 on the first qubit given a 1 on the zeros qubit is actually a half. So this is an entangled system because outcomes are dependent. Outcomes of measuring individual qubits are dependent. We will now finish with an unentangled state. So an unentangled state we will explore with psi is equal to, let's say, something that comes into mind. So we have two-thirds of 0, 0 plus root 2/9 of 1, 0 plus root 2/9 of 0, 1 plus 1/3, okay, of 1, 1. So let's check if the probabilities sum into unity. So we have 4/9, 2/9, 2/9, and then 1/9 over there. So it looks like the square looks like that. We now examine the probabilities. So probability of 0, 0 is 4/9. So probability of 0, 0, probability of 1, 0, probability of 0, 1, probability of 1, 1. So I referenced this so-called the square of a sum to synthesize this problem, create this problem on my head. So bottom of the learning pyramid. Now we have this demonstration of conditional probability. So probability of 0, provided that you have measured the zeros qubit to be 0, would be, in this case, what is the chance? So 0, 0, and 1, 0. So there will be like 6 outcomes which involve that. So it's 6. And then 4 out of 6 would give the second one to be 0. So it's 2/3. The probability of 1, 1 and the first qubit provided 0 in the zeros qubit would be 2/6 or 1/3. The probability of likewise of the 0 on the first qubit provided the first one on the 0th qubit would also be this. However, it will be straight up 1/3. The probability of observing both of them to be ones will be 1/9. Not to mention that the probability of measuring an individual qubit, any individual qubit, so the probability of measuring any individual qubit to be 0 will be this. Probability of 0 in the 0th qubit, probability of 0, 1, it is equal to this. So it's going to be just marginalize that. So six ninth likewise marginalizing probability of 1, 0 equal to 1, 1 would be 1/3. 2/3, 1/3. Then you multiply this together to form this thing. So it's equal to probability of 1, 0, and so on. So the state of this is unentangled. The outcomes are independent. This concludes our Easter special. And remember, God has risen. He has risen. And this would conclude the Easter special. And remember, this would conclude the Easter special. And remember, Jesus has risen.